In 2024, breast cancer became the most common cancer globally, primarily affecting women, although in rare cases it also affects men. Additionally, it became the fourth deadliest cancer after lung, colon, and pancreatic cancers. In the United States alone, in 2024, 310,720 women were affected by breast cancer, of which 42,250 cases were fatal. In this video, we will demonstrate how, using deep learning, it is possible for a trained model to correctly classify malignant breast cancer cases from others by simply inputting a mammogram. We achieve this using advanced image processing techniques based on a deep learning model with a visual transformer architecture. For this example, we will use the MAIAS dataset provided by the Cambridge Cancer Research Hospital. These data include key information such as patient identifier, background tissue type, type of abnormality, and severity of the abnormality. However, for our purposes, we will only use the images, the identifiers, and the severity of the abnormality. We will classify cases marked with an M as malignant cancer. All other cases will be treated as non-cancer. First, we organize the images into two folders, cancer and no cancer. After performing an initial exploration of the data, we can observe that the dataset is imbalanced, with 62.7% of the cases belonging to the cancer class and the remaining 37.3% to the no cancer class. This can be a problem when training the model, since if one class is predominant, the model may fail to correctly learn how to classify the less represented class. It is also necessary to split the images into subgroups in order to train the model. Most of them will be used for training, allowing the model to learn image patterns from them. A smaller group will be used to verify that the model is learning rather than memorizing, thus avoiding overfitting and ensuring that the model can correctly classify both the majority and minority classes. We will use 80% of the images to train the model and 20% to test it once training is complete. Before training, we must pre-process the images by cropping irrelevant areas, removing visual noise, and correcting saturation issues. Next, we apply image augmentation techniques to help the model generalize better and mitigate class imbalance. In this exercise, we used horizontal and vertical flips, rotations, and saturation changes to generate new images from the originals. Finally, all images are resized to 224 by 224 pixels, a standard dimension for image processing tasks. Now we are ready to train our visual transformer-based model. This architecture provides high accuracy due to its ability to capture complex relationships within images. As we recall from the previous season, the transformer architecture consists of an encoder and a decoder, but for this task, we only need the encoder since it is responsible for extracting relevant features from the images. At the end of the encoder, we incorporate a multi-layer perceptron, MLP, a simple neural network capable of performing precise classifications based on the extracted features. One of the main advantages of the visual transformer is that we only need to modify its original input to process images. For this, we divide each image into small segments called tokens. These tokens pass through a projection block that performs linear transformations, converting the segments into vectors. An extra learnable class embedding is then added, which helps the model learn specific patterns related to the entire image. These tokens are fed into the transformer encoder, where complex patterns are identified and related using the attention mechanism we discussed last season. Finally, the MLP generates the classification by activating the corresponding neurons based on the input image.